And once that starts, we're going to kick it off. All right, Chemistry 3111. This is our first chapter for the summer, and it deals with organic synthesis. And so what we're going to be mainly reviewing in this chapter, if you took Chemistry 3101 here at UCCS, mostly what we're going to be covering will be chapter 7, 8, and 9, and a little bit of 10. That would be the main focus of chapter 11. And if you wanted to narrow it down even more, it would be focusing on chapters 8 and 9. So chapter 8 in our textbook deals with the chemistry of alkenes, and chapter 9 deals with the chemistry of alkynes. So chemistry of alkenes and alkynes. Chapter 7 is SN1, SN2, E1, and E2. And then chapter 10 is free radical chemistry. All right, so let's get into it. And just give me one more second. There we go. All right, so if you have a question at any point, don't hesitate to unmute your mic and ask me a question, or simply type it in the chat and I'll try to keep an eye on that. All right, so section 11.11, or sorry, 11.1. What do we have to do? It says when we're solving a synthesis problem, or what we can simply refer to as providing the reagents, what you really need to master are your one-step or two-step reactions. And so if we look at a reaction like this one, here we have isobutylene. So this compound is called isobutylene. And then we're converting this to 1,2-dibromo-2-methylpropane. How do we do that? Well, for this reaction, we simply need bromine, Br2. And you should be able to draw the mechanism of this reaction. I'll put a little red star by that to denote you should be able to draw the mechanism of this reaction, right? You should be able to draw the bromine molecule, Br2, like this, and you should be able to push the curved arrows. I'm just going to draw the first step here, where you form the bromonium ion, and then the bromide comes in and attacks. Let me just ask you a little quiz question here. The bromination reaction, does it occur via syn addition or anti-addition of the bromine atoms? Could anybody answer that in the chat? Yeah, it's anti-addition, isn't it? Anti-addition, absolutely. So again, when I put that little red star, that means you should be able to draw that mechanism. And that mechanism is covered in detail in chapter 8. So if we go all the way back to our chapter on alkene chemistry, it says here, identify the reagents that can be used to accomplish each of these transformations. And again, if you're struggling with any of these, where can you find more information? It would be in chapter 8. But this is kind of the bare minimum, and I don't mean that in a mean way. This would be kind of the bare minimum of what you need to know in order to proceed into organic chemistry 2, the class you're currently enrolled in. So if we start with this reaction here, if we want to take 1-methylcyclohexene, so that's this alkene, and we want to convert it into 1-bromo-2-methylcyclohexane, what would be the reagents that I would use here? First of all, I want to ask you, is this a Markovnikov addition of HBr across the double bond or anti-Markovnikov? Could anybody answer that? Yeah, this is an anti-Markovnikov addition, isn't it? Absolutely. And so to do an anti-Markovnikov addition of HBr, could anybody tell me what reagent I need besides HBr? So I need hydrogen bromide, and what else? Exactly. I need some kind of organic peroxide. So I'll put ROOR here. And again, that represents our peroxide. Let me just clean that up like that. There you go. So that's an anti-Markovnikov addition. So we'll put here anti-Markovnikov addition. And if you're wondering, where do you look, where would you find the mechanism to that reaction? That's found in chapter 10. So I'm going to put here a little star by that, and that is found in chapter 10. This is a free radical reaction, which follows the steps of initiation, propagation, and termination. What about the next reaction? So if I want to do this one, would that be a Markovnikov or anti-Markovnikov addition of HBr? Anybody? Absolutely. This is a Markovnikov addition of HBr. So I'm just going to pencil in here. I'll just kind of write it up here, HBr, like that. There we go. So HBr. Let's take a step back and take a look at this reaction here. If I want to take methylcyclohexane, so that's this compound, and if I want to convert it to 1-bromo-1-methylcyclohexane, what would the reagent be here? Could anybody help me out with that one? I just want to brominate an alkane. Thanks, Jaylin. Absolutely. It's going to be bromine and light. Another option would be bromine and heat. But yes, bromine and light will definitely do the trick. So we'll put here bromine. We'll put H nu, that represents light. Then we'll put here or heat. Either one is perfectly acceptable. And remember, that's also a reaction that's found in chapter 10. It's free radical addition of bromine to a hydrocarbon. Let's try this one here. What if we wanted to do an elimination? First, let me ask you this question. The reaction that I have in this black oval here, would this be taking the alkyl halide and making the Zaitsev product or the Hofmann product? How would you describe this alkene? Would that be Zaitsev or Hofmann? Yeah, that's right, Tiana. It's the Zaitsev product, isn't it? Right? Right. The Hofmann product, you'd have the double bond here. Okay. And so if we want to make the Zaitsev product, we're going to use an unhindered base like sodium methoxide. So we'll pencil that in here. If you did this one before you came to class today, and if you wrote sodium methoxide, that's totally fine. There's nothing wrong with that. Let's try something else here. Let's try something really crazy. Let's try this reaction. If I want to take the alkene and open it up so that I get this ketone and aldehyde in the same molecule, what kind of reagents would I need to do that reaction? I want to split that alkene open. Yeah, absolutely. Absolutely. So this is an ozonolysis reaction. So step 1 is going to be ozone, so O3. In step 2, since we're doing the ozonolysis of an alkene, that would be dimethyl sulfide, yes, so dimethyl sulfide. The other option is zinc and water, but that's not used very widely in our textbook, so we'll leave it at that. Let's move on. I'll use the red pen again. What about this one? Would you describe this as syn dihydroxylation or anti-dihydroxylation? Not a trick question. It's syn, yes. Okay, so I taught you, if you took organic chemistry 1 with me, or if you took it with Dr. Anderson at UCCS, or maybe with Dr. Schaafstal, whoever, you would have learned a few ways of doing this reaction. Can anybody just throw any reagent at me? Yeah, absolutely. So potassium permanganate will work, sure. Yep, that's one option. I'm going to pencil that down, Audrey, since you colored that out first. So KMNO4, sodium hydroxide, and that's done at low temperature. I'm going to put an arrow over here, though, Audrey, and say, anybody have any other options for this one? Do you guys remember osmium tetroxide? Yes, absolutely. So I'm going to put here osmium and something. That's right, osmium tetroxide. And that's just a catalytic amount. And NMO, which stands for N-methylmorpholine N-oxide, which is the co-oxidant. And I see that Tiana put, you're close, you put sodium bisulfate. It's sodium bisulfite, so SO4. That also works. I would also say totally acceptable. Yes, absolutely. All right, so that's syn dihydroxylation. Does anybody remember the conditions for anti-dihydroxylation? This reaction here. I want to do anti-dihydroxylation. This is actually a 2-step process. Anybody? This one? All right, I like the way you think, Maria. It's a peroxy acid in something, right? So the first step is a peroxy acid. We'll put here RCO3H. Step 2 is aqueous acid. So just aqueous acid will crack open the epoxide. All right, move on from there. So this one here, this is halohydrin formation. So halohydrin formation. So what do we need to do that? Well, we need to have bromine, which forms our bromonium ion, but we use water as the solvent. Because water is our solvent, it comes in as a nucleophile and attacks the bromonium ion and gives us the halohydrin. The next one, we already looked at that one. It was one of the first reactions we looked at, which is just bromine. So just bromine. What about the next one, where we take an alkene and we convert it to, I'm kind of circling the wrong, an alkene to an alkane. What kind of reaction would we use for that? Yes, absolutely, it's hydrogenation. So hydrogen and platinum, palladium, or nickel, any one of those will work. The next one is the anti-Markovnikov addition of water. Does anybody remember the conditions for anti-Markovnikov addition of water? Anybody? Anti-Markovnikov. Somebody had written it earlier. Yes. So this is borane and THF. So we'll write step 1 is BH3 and THF. Step 2 is hydrogen peroxide and sodium hydroxide. Absolutely. And the last one is just a Markov-Nikov addition of water. So we'll just put H3O plus on here. All right. And that pretty much covers the gamut of reactions that were learned in chapter 8. So you need to have all of these reactions. No, you have to know all of these off by heart without any kind of wavering or anything in order to move forward in the class. If you're wondering which ones do I have to have the mechanism down for, I can help you out with that. I would say the ones you should be able to draw the mechanism for with relative ease would be, how will I do this? I'll put a little star over the reagent. So this one, the elimination, the Markov-Nikov addition of HBr. I'd say the halohydrin formation. I'd say bromination. You should know that one. And of course, Markov-Nikov addition of water. You should know that. The bromination, I mean, I probably won't ask you this one, but it is one that we did go over in detail. So I'll put a blue star by that. And there's one reaction that we learned that I can think of off the top of my head in chapter 8 that's not shown on here. So I'm just going to write down the reagents, which is mercuric acetate in water, followed by sodium borohydride. And this is what we call oxymercuration demercuration. Does anybody remember what this reaction was used for? Yeah, absolutely. Absolutely. So this reaction is used for the Markov-Nikov addition of water. So Mark addition of H2O. However, we avoid carbocation rearrangements. So I'll put C plus rearrangements. So that's when you would use oxymercuration demercuration. That's the only reaction that's not shown on here. And it could be used for this reaction. However, we like to avoid using mercury when we can. All right, any questions about any of those reactions before we move to the next slide and talk about alkyne chemistry? Any questions about those? All right, so again, you want to know all of these reactions, frontwards, backwards, sideways. You don't want to be sitting around and humming and hawing about these. You really want to know these in order to move forward. And you know, what's the best way to remember these? Well, it's probably a little bit different for everybody, but I would say practice of synthesis problems is probably, you know, my preferred method and one that I've seen students have continued success with. Okay, so that's the first question. Let's move on to the second question. It says, identify the reagents that you would use to accomplish each of these transformations. If you're having any trouble, the reagents for these transformations appear in the review of the reactions at the end of chapter 9. So chapter 9 deals with the chemistry of alkynes. And so, yeah, let's see if we can, you know, give some of these the old college try. So, you know, you need to know your alkyne nomenclature. Could anybody name the compound at the center here? Could anybody name that compound? How would you name this compound? It's got 3 carbons and 1 triple bond in it. No, it's not acetylene. So acetylene would be just 2 carbons, right? This is, that's a pretty bad drawing of it. Well, this would be acetylene. It would be propylene, exactly. Propylene or propine, either way is totally fine. Yeah. Thanks, Avishai. So, yes, this is propylene. All right, or propine. Either one is acceptable. All right, where should we start? I guess we could start anywhere. Why don't we start here? If we want to take propylene and we want to add HBr to it in a Markov-Nikov fashion, the reagent that we would need to do that would be HBr. So I'm just going to put HBr. And if you really want to get down to the nitty-gritty, you could say, you know, 1 equivalent, which means 1 mole to mole ratio, and that would be totally fine. If you just wrote HBr, I would understand that as well. In the next one, if we want to take the monobrominated compound and we want to add a second equivalent of HBr to that, we could just say HBr again. All right, nothing more than that. Okay, So let's say we had either this geminal dibromide or this vicinal dibromide, and we want to convert it to the alkyne. Very important chemistry, being able to take a dihalide and convert it into an alkyne. Does anybody remember what the conditions are for that? Both of these reactions would would require the exact same reagents. Does anybody remember how to do this double elimination? Yes, you're definitely on the right track. Absolutely, yes. So what my students are saying is this. Let me just try to get these green circles off of here. Is that the first step is going to be excess sodium amide, right? Because that does the double elimination. And then the last step, I would agree with you, Chaylin. I would say H3O plus or H2O. I think the textbook just says H2O, so I'm going to leave it that way. But if you wrote H3O plus, I'd be okay with that. And so I'm going to put my red star by that right now because this is a mechanism you need to know. A double elimination followed by a protonation. Very, very important reaction mechanism that you need to know. Double elimination followed by a protonation. If you're wondering, well, where would I find the mechanism for that? You're going to find it way back in chapter 9. So that's something that should have been learned in Organic Chemistry 1. All right, let's try something interesting here. What if we want to take the propine and convert it into acetic acid and carbon dioxide? There we go. Yes, this is an ozonolysis reaction. So the first step is going to be ozone. And unlike an alkene, where the second step is DMS, our second step here, it just uses water. Great. All right, thank you, Audrey, for that one. Let's kind of go backwards here. What if we wanted to take propine and add all the bromines in the universe, it seems like, to this thing? What would we use for that reaction? All we would need is an excess of bromine, nothing more than a whole lot of bromine. So excess Br2. If you want to put a solvent in, like carbon tetrachloride, that's fine. If you want to leave it out, that's fine too. It doesn't really bother me. And so if we would use excess to add 4 bromine atoms, it stands to reason that if you only want to add 2, you would just write, 1 equivalent of bromine to make this trans dibromide here. All right, let's talk about some reduction reactions. What if we want to take, let's do the addition of an alkyl group here. So if we want to take our propine, which has a hydrogen on the end, it's a terminal alkyne. If we want to add 1 carbon to the skeleton, how do we do that? It's a 2-step process. Anybody could guide me through that? Yeah, absolutely. The first step is going to be to use a strong base like sodium amide to do the deprotonation. And then in the next step, we add methyl iodide, or you could put methyl bromide or methyl chloride as the electrophile, and that's going to add the carbon. And so if we want to reduce that alkyne completely down to the alkane, we would just use, where's my screen? We would just use hydrogen and palladium, platinum, or nickel. What if I want to reduce it to the trans alkene? Anybody could help me with that one? If I want to make the trans alkene, I'll make the trans alkene from the alkyne. Yes, liquid ammonia, exactly. So what Avishi is saying, she's saying use sodium metal reduction in liquid ammonia. Oops, I don't know what I'm putting there. NH3, liquid, yep. And then if I want to make the cis alkene, you probably remember that you use Lindlar's catalyst. So we'll just put here, good. Thank you, Maria. So Lindlar's catalyst to make the cis alkene. The next reaction, to make an aldehyde. We're going to learn many ways to make aldehydes in organic chemistry too, but I only taught you, I guess, kind of 2, because we learned ozonolysis of an alkene. But I only taught you 1 way to make an aldehyde from an alkyne directly, and that's to do the anti-Markovnikov addition of water. However, when we do anti-Markovnikov addition of water to an alkyne, we don't use borane, but we use 9-BBN, which is our hindered borane. And then in the second step, we use H2O2 and sodium hydroxide. And what that does is it gives us an enol. It actually gives us this enol, and then it rearranges to give us the aldehyde. Could anybody tell me the name of that rearrangement process? It's got a tsatsi name that starts with the letter T. Yeah, tautomerization, absolutely. And then the last reaction is where we do the the Markov-Nikov addition of water across a triple bond. And to do that, we use sulfuric acid, water. And in order to get that reaction to go, we have to put in mercuric sulfate, so mercury 2 sulfate. And that would give us, this enol. This is Markov-Nikov. And that will undergo tautomerization to give us the methyl ketone. There you have it. So let me see. Besides the two that I put the red star by, the other ones I think you should know the mechanism for. I don't know. I would put by the alkylation. So you should know that one. And that's probably enough. As long as you know those mechanisms, you should be pretty rock solid moving forward. So what did we just cover in question 11.1? In 11.2, we covered the chemistry of chapters 8 and 9, or at least we covered the vast majority of it. So again, I'm not saying this to sound like a meanie or to try to intimidate you or anything like that, but if you want to be successful moving forward, you have to know these reactions frontwards, backwards, and sideways. Give me a thumbs up if you're with me on, let's say, I don't know, 75% of these reactions. Anybody 75% of the way already? Great. Awesome. And I'm sure that some of you are probably 100% of the way, and that's great. But if you're lagging a little bit, make sure you take the time to go over these this afternoon. You know, one strategy that my students had used over the years is to print out question 11.1 and 11.2 just on a blank sheet of paper. Just print it out maybe 10 times and just keep trying them over and over and over. All right, there we go. So let's say we have a question like this. If I ask you to move a functional group, okay, let's say I ask you to move this bromine in this 4-carbon compound, and I ask you to move it, 5-carbon compound, and I ask you to move it over here. You know, how would we do that? Well, you see that the first step is an elimination. So you can see that we do that elimination to make the Zaitsev alkene. And so if I want to choose a strong base, my question to you is, am I going to choose a hindered base or an unhindered base if I want to make the Zaitsev alkene? Would it be hindered or unhindered? Exactly, it would be an unhindered base. So a good choice would be something like sodium ethoxide, right? And then for the next step, you can see that we're doing a Markov-Nikov addition, and we just went over this, that if you want to do a Markov-Nikov addition of HBr across a double bond, all you need, the Beatles said all you need is love, but I say all you need is HBr, and that will give you the Markov-Nikov product. And so you can see that very quickly we can outline a synthesis, and this is exactly what we just did on the previous slide. Now let's say you took this starting material and you treated it with a hindered base, like potassium T-butoxide. In that case, you're going to end up with the Hoffman. So this is the Hoffman alkene. And if you took that Hoffman alkene and you did an anti-Markov-Nikov, so this is an anti-Markov-Nikov addition of HBr, well, then you're going to move the bromine from this carbon in yellow over to this carbon that I have highlighted in green. And so you can see that we're able to put it on any of those carbons. This one that I have highlighted in blue, the yellow one, or the green one. Through the magic, quote unquote, of organic synthesis, we're able to move a functional group around. But the only way you're able to do this is by knowing all of the reagents on this page and knowing how to use them and when to use them. Now, let's say you up the ante, and instead of having a bromine, which is a good leaving group, what if you had a hydroxyl? Is hydroxyl a good leaving group? Is hydroxyl a good leaving group? Absolutely not. Could anybody unmute their mic or maybe type it in the chat and tell me, how do you know something is a good leaving group? How do we just evaluate something and say it's a good leaving group without memorizing? And I guess there's some memorization involved, but how do you know, how can you say it's stable conjugate base, right? So it's going to be the conjugate base of a strong acid or a weak acid. It would be the conjugate base of a strong acid or a weak acid. I have a good leaving group, and I look at that leaving group. Is it the conjugate base of a strong acid or a weak acid? It's the conjugate base of a strong acid. Absolutely it is. Yes. Conjugate base of a strong acid. So just to go on in a little more detail about this, the reason why hydroxide isn't a good leaving group, because hydroxide is the conjugate base of water. Water is not a strong acid, right? But if let's say I protonated this hydroxyl, let's say I converted this to OH2 plus, I made it an oxonium. Well, in that case, the leaving group would be water, which is the conjugate base of H3O plus. Is H3O plus a strong acid? Yes. And so if we could protonate it, it would be a good leaving group. However, what they're showing on this slide here is not converting it to an oxonium, but rather converting it to a tosylate. So if we treat the hydroxyl group with tosyl chloride and pyridine, sorry, just the first step, what that does is it makes a tosylate. So I'll draw the tosylate up here. You would just say OTS, and the tosylate is a good leaving group. It's the conjugate base of toluene sulfonic acid, which is a strong acid. And so then we can do an elimination. We can do an elimination with an unhindered base to make the Zaitsev alkene. We could do an elimination with a hindered base to make a Hoffman alkene. And from that, we can add water in a Markovnikov fashion or an anti-Markovnikov fashion. And you even see here them taking the Zaitsev alkene and treating it with oxymercuration, demercuration conditions in order to add water in a Markovnikov fashion, but and also to avoid a carbocation rearrangement. So make sure you're aware of all the reactions on here. So one that we didn't touch on is the conversion of hydroxyl to a tosylate using tosyl chloride and pyridine. So let's say we want to move a pi bond around a molecule. If we want to move the pi bond from inside this ring, so this would be called 1-methyl cyclohexene. And this is called methylene cyclohexene. Anyhow, the name is neither here nor there. So if you want to convert it to methylene cyclohexene, how would you do that? First, you would do a Markovnikov addition. So this is a Markovnikov addition of HBr across the double bond. And then our elimination, for this elimination reaction, will we use a hindered base or an unhindered base? Could anybody help me out with that one? Absolutely, we'd used a hindered base, like potassium T-butoxide, right? And that's going to give us our elimination reaction. And keep in mind that you should be able to draw the mechanism of an E2 reaction, right? How would you draw that mechanism? Well, if we zoom in here, let me just erase this and I'll just draw the potassium T-butoxide. So here's my T-butoxide. All right, I'll draw my potassium up here. So we have our alpha carbon here. This is our beta carbon. There's the proton that's going to be abstracted. So we're going to do the proton transfer, form the double bond, and lose the leaving group. And that is our E2 reaction. Everybody who's hearing the sound of my voice should be able to draw a mechanism, an E2 mechanism like this, without great difficulty, right? These are things that we should be able to do. All right. So with that in mind, let's take a look at some functional group transformations that we have shown here. And there's only so much yammering on I can do about these kind of slides because, and these are Dr. Klein's words, not mine. It says we have no chance on getting any of these questions right unless you can easily recall all the possible reagents and reaction conditions first. So that's a politically correct way of saying you have to have all of your reactions memorized first before you can move forward in the class. All right, I'm going to skip this slide and let's take a look at some reactions. So let's take a look at the first two and then we'll take a short break and I'll see if you can tackle some on your own. So let's say we want to do A. Let's see here. Okay, let's say we want to tackle A. So come on, there we go. We want to convert this alkene into an alkyne. So are we changing the carbon skeleton at all? Is there any change to the number of carbons as we go from the starting material to the product? No. So there's no change there. And so if there's no change, really, you could do a retrosynthesis here because the only way that you know that I would have taught you or Dr. Anderson or whoever would have taught you how to make this alkyne would be from what? Could anybody describe it to me without me just telling you the answer? I'm sprucing this up. What would that alkyne have to come from? We can't make it via alkylation because we're not changing the carbon skeleton. The only place this could come from is what? Anybody? Where would this have to come from? No, it's not hydrogenation. So look, let's go back. Let's go back here to question number 2. Right? The only place that an alkyne can come from is from either a geminal dihalide or a vicinal dihalide. And the only thing I ever taught you how to make is a vicinal dihalide like this. So you'd have to employ those reaction conditions. So that means it's got to come from a dihalide. So let's go back here. It's got to come from this compound. It's the only possibility, my friends. The only possibility is it has to come from that. And so how do I convert this alkene to this dihalide? Anybody? What would my reaction conditions be? Exactly. It's just going to be bromination, right? So I'm going to take this and I'm going to treat it with bromine, and that's going to give me the compound in red. Once I have the compound in red, then I can, like Tiana says, I can treat it with excess sodium amide to do the double elimination. So where's my, there, excess sodium amide. And then in the third step, I'm going to put water in there to do the protonation. All right, it's the only possibility for this reaction. Just give me 1 second to scribble something down here for myself. So let's go to a blank document just for a second. Let's see here. There. Let's just go to a blank document and let's talk about the expectations here of what you should be able to do with a question like this. So if you have this alkene that we just started out with, you should be able to draw the mechanism of the bromination, right? You should be able to draw the molecule of bromine, so which looks something like this, and draw the mechanism of the formation of the bromonium ion. So I'll draw the bromonium ion, which is going to look something like this. All right, now whether it's syn addition or anti-addition is really irrelevant here because you're going to do the double elimination on it anyway. But you should know that the next step is where the bromide comes in. So let me just draw my bromide, this, and then the bromide is going to come in as a nucleophile. It's going to attack here, and we're going to end up with our dibromide. So we have that like this. The next part is we're treating with excess sodium amide. So what is sodium amide? Can anybody tell me, is sodium amide an acid or a base? This excess NaNH2, is that an acid or a base? Yeah, it's a base. It's a very strong base, right? So what we're going to do is we're going to take the amide ion, okay, which is a strong base, and we're going to start doing the eliminations. So we could start by ripping off this proton. So we're going to remove the proton, lose the leaving group. That's going to give us this compound. So we're going to end up with something that looks like this. All right, so we've lost HBr, right? We've lost HBr in the process. Then the second equivalent of sodium amide, because it's excess sodium amide. So the second equivalent is going to pull off this proton. So we're going to rip off this proton from the double bond, lose the leaving group. We're going to end up with the triple bond. Okay, but are we done? No. Could anybody tell me what's going to happen in the next step of the mechanism? There's a third step here with the sodium amide before we can move forward with the water. Anybody know what's going to happen in the third step? Okay, so in the third part, we're going to rip off the proton, right? So the last equivalent of sodium amide, here's my amide ion, is going to pull off this proton and make the alkanide. And that is actually, I'll put an arrow going like this. This is actually the driving force of the reaction, is the formation of the alkanide ion. Okay, so this is what you get from the excess sodium amide. And then in the very last step, when you treat it with water, the water is a source of protons. So the alkanide is going to pull off the proton to give you the final compound, like that. So that's the whole entire synthesis, and that's the mechanism. And so you should be able to draw these kinds of mechanisms, right? The first one is the E2. This is an E, or sorry, the first one is the bromination. So from here to here, this would be bromination. Bromination. All right, this one is the E2. From here to here, I guess. And then this last step is just the protonation with water. So again, first step is bromine. Second step is excess sodium amide. And the third step is water. And so you should be able to draw the mechanism of E2, the mechanism of alkylation, and that kind of thing moving forward. Any questions about that mechanism? It's covered there. Trying to squeeze it all on one page, kind of tough to do. All right. Well, let's go back here into the lecture material. So where were we? All right. So why don't we take a short break? And I'm going to let everybody take a chance to tackle questions B, C, and D. And then we'll come back and see how we did on those.